This video will accompany Chapter 3, Section 1 notes. In Chapter 3, we're going to look at association, contingency, correlation, and regression. In this chapter, we will discuss how two variables might exhibit a pattern with one another, but that does not imply that one of the variables directly influences the other. It is often the case that we would like to know about the relationship between two variables. You've probably read about studies involving two variables without realizing it. Visit the health section of any major news outlet and you will find an article like this one. Take a moment and read this part of the article. The news article is looking at the relationship between the following two variables: type of marijuana laws and number of opioid prescriptions. To determine if the two variables are related to one another, we must first determine how the two variables may be interacting with one another. We usually identify one of the variables as the explanatory and one as the response. We need two different definitions. The explanatory variable is the variable which will help us understand values of another variable. It is known as the independent variable. In the news article, where a state has a marijuana law would be the explanatory variable, since the researchers are looking to see if marijuana legalization can change opioid prescription patterns. In this picture, the explanatory variable would be whether or not the stove is hot. The response variable is the variable we want to observe change in based on the explanatory variable. It is known as the dependent variable. In the above news article, number of opioid prescription patterns would be the response variable, since the researchers are looking to see if the number of prescriptions change based on whether the state has marijuana laws. In this picture, whether or not the person is injured would be the response. Notice that whether or not they are injured touching the stove depends on whether or not the stove is hot. Therefore, whether the stove is hot is the explanatory. There are also two different kinds of relationships that we need to distinguish. Two variables are associated if the values of one variable exhibit a pattern with values of the other variable. Associations are visual. We can see an association by looking at a plot or comparing numerical summaries. Associations do not necessarily mean that one variable has a direct influence on the other. Causation occurs when one variable directly influences another variable. The distinction between association and causation can be tricky. The key is to remember that associations are only visual. Understanding the distinction can be hard for people because when we see a visual pattern, we tend to think that there is some underlying cause for the patterns. Suppose a scientist recently saw the Snickers commercial featuring sharks who love Snickers and become concerned that people who eat Snickers ice cream are more prone to shark attacks. If you haven't seen this commercial before, follow the YouTube link to watch it. The scientist has little funding and cannot perform a proper experiment, so he gathers data on the number of boxes of Snickers ice cream sold and the number of shark attacks in the same coastal region. He then creates the following time plot. First, it should be noted that this is a terrible graph, and from Chapter 2, we learned about techniques for making easy-to-read and informative plots. So we want to start by identifying the explanatory and response variable for this example. The explanatory variable here would be the number of ice cream sales, whereas the response would be the number of shark attacks. By looking at the plot, notice that the ice cream sales and number of shark attacks exhibit a similar pattern over time. This is an example of an association. The variables ice cream sales and number of shark attacks are associated because over time we can see that they exhibit a similar pattern. Later we will look at different types of associations. What we are interested in learning is, do ice cream sales cause shark attacks? The obvious answer here is no. Realistically, we know that ice cream sales do not cause shark attacks. It turns out that many variables will exhibit patterns over time, but there is no causation. Sometimes it's easy to determine that there is no causation. For example, consider this plot. This plot is making a comparison between the number of films Nicolas Cage has appeared in and the number of people who drown in a swimming pool. Notice that these two variables have a similar pattern over time. Thinking rationally, you can see it's obvious that the number of films Nicolas Cage appears in has nothing to do with number of drownings. Other times, it's much harder to determine that there's no causation. Consider this plot. This plot is making a comparison between the number of individuals diagnosed with autism and the sales of organic foods. Notice again that the variables have a similar pattern over time. This is a case where it's not obvious that causation is not present. When looking at plots, many people are tempted to conclude that the two variables are linked since there is a pattern, and it's not obvious that there's no causation. This is not the case. Remember that associations do not determine causation, and this brings us to an important rule. No matter how clear the pattern between two variables on a plot, you can never use a plot to determine causation. This brings us to section 3.1, the association between two categorical variables. We may want to compare two categorical variables. To investigate a possible relationship between two categorical variables, we will use what's known as a contingency table. A contingency table displays the relationship between two categorical variables. The categories for one variable are listed down the left, and the categories for the second are listed across the top. Each of the cells of the table contain a count of number of cases that are both row and column categories. For example, suppose that researchers are interested in comparing a person's diet to health outcomes. They decide to compare the Mediterranean diet to the American Heart Association's recommended diet. The following data was published in the article, Mediterranean Diet Patterns in a Randomized Trial. We can answer different questions using this table, such as, how many people were in the study? How many people developed cancer? How many people ate the Mediterranean diet? And how many people on that Mediterranean diet developed fatal heart disease? So let's look at each of these. In order to determine how many people were in the study, we can use the two totals. Notice this total column here and the total row along the bottom. This column tells us about the totals of people that ate the two diets, whereas the total row on the bottom tells us about the total people that had each of the health outcomes. The bottom right-hand quarter tells us the totals of people overall, and so notice in this case there were 605 total people in the study. How many people developed cancer? Looking at the cancer column, we can see that there was a total of 22 people who developed cancer. How many people ate the Mediterranean diet? We can use the row corresponding to this type of diet to find that the total is 302. And then finally, how many people eating the Mediterranean diet had fatal heart disease? Well, we can see where the diet and the fatal heart disease match up to see that there are 14 people matching this. Conditional proportions depend on one of the variables having a given value. For example, we may be interested in the proportion of people on the Mediterranean diet who develop fatal heart disease. Here we are conditioning on the person eating the Mediterranean diet since their information is conditional. Looking at the table, what we're saying is that we're restricting ourselves to this row of the data set. So we're only looking at those people that ate that diet type. So we're conditioning on the person eating the Mediterranean diet. Since their information is conditional, the proportion can be calculated as 14 divided by 302. In situations where we distinguish between explanatory and response variable, it is natural to form a conditional proportion based on the explanatory variable for categories in the response. In this scenario, diet is explanatory. Marginal proportions are calculated using the overall total and are not conditional. The proportion of people who ate the AHA diet is not a conditional proportion. So for example, we could look at the right-hand total here. Notice this has nothing to do with health outcome. It's only looking at the information on diet. And we could see that if we were interested in the proportion of people eating the AHA diet, we would have 303 divided by 605. Now it's your turn. On the top of page 6 of your notes are 4 bullet points. For each of those, calculate the requested proportion and decide if it is conditional or marginal. Pause the video, and when we come back, we'll look at the answers. Were you able to find the following? There are several different types of graphs which can be used to visualize the relationship between two categorical variables. We could display proportions of outcomes for each diet separately, side by side, or we could combine all the information in a stacked bar graph. These plots can help us look for associations. Here we have a side-by-side bar graph. The height of each bar is the number in the corresponding cell in the two-way table. Take a moment and confirm these amounts. We can also look at a stacked bar chart. It's like a side-by-side bar chart, but the bars are stacked instead of side-by-side. Again, take a moment and compare these values with the two-way table. It appears that there is a weak or moderate association between diet and health outcome. There would be no association if instead the proportion with different health outcomes would have been equal for each diet. Caution: when sampling from a population, even if there is no association between the two variables in the population, you can't expect the sample conditional proportions to be exactly the same because of ordinary random variation from sample to sample. Later in the text, we'll present inferential methods to determine if the observed sample differences between conditional proportions are large enough to indicate that the variables are associated in the population. A difference in proportions is a difference in the proportion for one categorical variable calculated for different levels of another. A difference in proportions calculated from sample data is denoted as p hat 1 minus p hat 2, where 1 and 2 distinguish the different groups. A difference in proportions calculated from population data is denoted p1 minus p2. On the top of page 8 of your notes is a problem for you to try on your own. Find the difference in the proportion of people on the AHA diet who develop cancer versus the proportion of people on the Mediterranean diet who develop cancer. You can denote this by p hat A minus p hat M. Take a moment and try this on your own, and when you come back, we'll find the answer. Were you able to find the following? Then notice we could simplify this to this value. This concludes the video on section 3.1.